is a member of the founding team for IIT Hyderabad and served as an inaugural chair to set up the computer science department at IIT Hyderabad. He has upgraded the unit of the Indian Statistical Institute in Chennai to a center and served as inaugural chair for the ISI, Chennai Center. He is a fellow of the Indian National Academy of Engineering from 2006. He was honored as Venki Harinarayan and Anand Rajaraman Chair Professor in 2017. He served at IIT Madras until his retirement and superannuated in 2021. Since August 2021, he served at IISc in the Department of Computer Science and Automation as Satish Dhawan Visiting Chair Professor. He will be talking about puzzles and paradoxes for algorithmic thinking. Over to you, Professor.
Thank you very much. I love this first talk after the lunch. Right? Crowd will be sparse. After a food, you will be a little more relaxed and philosophical. I won't get hard questions. What else you want for a speaker? This is the ideal situation in which you can talk. Okay, we are in the art of computing. How do you learn any art? How do you learn any art? Practice. Okay, first, that's a nice thing. What do you practice on? Suppose you want to write poem in Bengali, right? How do you start? Where do you start? Learn the language, okay? The point is, there is no systematic way of learning any art. There is no one way of doing it, right? And more importantly, there is no way of teaching the art. It has to be learned. How can I teach you to write a poem? It's an inspiration that should come from within. I can give example. I can quote Rabindranath Tagore, or I can quote Tirukkural, or I can quote some great Indian poems. And I can give only examples. The inspiration should come from within. How do you get that? Okay? In general, for learning anything, especially creative things, the basic thing that we have to do is thinking. We need to think. It is something connected with creativity. Your mind should work at it, right? Different bodies of knowledge have got different styles of thinking. Take a civil engineer, okay? He's going to think, he's going to look at the world in a different way. Look at the doctors and the practitioners. They are going to look at the human body and the system in which it works and everything, interpretation of pain, and completely different set of thinking, right? What's our mission for computer scientists? Solving a real-world problem using a computer. We have solved a lot of real-world problems, even before computers. We have built Tanjore Brigadeshwara temple, put up a dome 160-meter high so that the shadow of it never touches the base. Imagine the elliptic movement of the sun, and an object kept its shadow and its length, calculation of all of them. Everything has been done. And it is there even now as a UNESCO World Heritage. It's in Tanjore, southern part of India. If you haven't visited, you should go there and see. Simply lose yourself in the amazement of the creation, right? So many wonders of the world have been created like this. Great thinking they have done, right? So what is important is everything. We have solved the real world problems. We have used mathematics. Math. First of all, if you want to solve any problem other than some trivial ones, you need to recast that in a mathematical framework, recast that as a mathematical problem, visualize this in a mathematical model, physical model or conceptual model. Somebody throws a stone. How high it goes and where does it land? We have seen that. We throw stones and it goes somewhere and it lands. But in order to analyze it mathematically, you have to set up an appropriate equations, the laws of motion, everything you have to apply, and then you set up math. Immediately math comes. Therefore, for solving any real-world problem, the first thing that you do is mathematical thinking, right? I'm going to talk about algorithmic thinking. What is the basic difference between mathematical thinking and algorithmic thinking? Math is concerned with the rigor, with the validity. It should be true. It should be valid. Therefore, it will focus a lot more on the properties, validities, proofs, and so on. That's the role that math should play. You can't work with nonsense. You cannot simply try to build a multi-story building without understanding how much foundation you have to dig deep for. You need proper answer for that. You can't take some wild guess and then start doing things. You need rigor, you need math, you need proper things. Everything that math will provide. But when it comes to solving the problem using computers, we require a slightly different kind of a thinking. That's what I'm going to focus on. This is called the algorithmic thinking. Right? Still the focus is on problem solving, using math, everything will be there, but we are going to give an engineering twist to that. That is called algorithmic thinking. We would like to solve, okay? What is involved in algorithmic thinking? Algorithms, as you all know, is the backbone of, it's a backbone idea behind any solution that is implemented. Any software that works has got an algorithm behind it. That's an underlying idea, okay? And you have to create an algorithm. Therefore, this is a creative task. This is something that you do. How do you create an algorithm? How do you solve math problem? How do you... So one thing that we see, the Mother Nature has given us a way to begin with certain things, right? How do you think a lion or a tiger cub learns the art of hunting? Do you have a IISc or IIT for hunting and then they write an entrance exam for... They don't do that. How do they learn? The mother tiger will feed the cubs for 6 weeks, 8 weeks, and after that it will be abandoned. After that it has to hunt. Who is teaching that? Nobody. How does it learn? Observation, right? When they are young kid, they follow the elders, uncles, mother, father, whatever it is, and then they strategize. They watch the strategy. They hide behind the bush, they team up, they attack this way, they pounce at this point. Some abstract wisdom from that is to be extracted. If it simply repeats, if it hides behind the same bush and wait, will it get food? It may not. So what it should do is, from various observation, it extracts the wisdom and tries to customize it, because it is going to be in a different place. Therefore, hunting as a pattern, it absorbs and then customizes and applies to solve the problem, current problem in the hand. Okay, it is seasonal, it is not everything, every time it is going to get a deer. So various things, various options, various ways it has to do, extend. Same way, the algorithmic thinking also should begin with certain observation. What is that you have to observe and how do you strategize? And what are the things that are involved in this is what we are going to see. So we are going to take a simple case study using a puzzle. The reason why I am taking the puzzle is to keep the things as common as possible rather than taking a domain-specific case study, which would probably be appreciated by the people who know something. If I take an example from graph algorithms or computational geometry or something like that, or cryptography, it would probably connect only a few people. But when it comes to puzzle, anyone can understand, instantly connect, and then grasp the idea. That's the way, that's the reason why I made this interaction puzzle-centric. Our focus is going to learn the art of computing, or the strategies for learning the art of computing, specifically in the context of computer science, algorithmic thinking, and towards that, I'm going to open up an interaction with you. Okay? So there are 3 big jars. Okay? They have A liters of water, B liters of water, and C liters of water. Okay? There are 3 jars. They have A, B, C liters of water. Integers. All are integers. A, B, C are integers. Now you have to empty one of them by doing the following operation. Okay? So a task is to be performed and you are given an operation that is used. Very typical in computer science. Sorting. You don't take square root, multiplication and other things. Okay? You do comparison. as a primitive operation and then try to solve the problem. Okay? In general, in computer science, abstract data type, a mathematical model together with some set of operations, and that sets the goal or the framework for you to solve the problem. You start with that. Now, in general, in computer science, when a problem is given and an abstract data type is specified, you use those operations cleverly and then arrive at a solution for it. For example, if the question is, what day is 113,000? Is it Wednesday or Thursday? If this is a question, if you want to write a computer program, now you go to a different world, an abstract world, a new math world called the calendar. There you have entities like January, February, and so on, March, leap year, Sunday, Monday, and there are some rules for arithmetic, some operations defined. In terms of those operations, you try to solve the problem. It's always the challenge for computer scientists. The problem is to be solved. A set of operations and tools will be available. Resources will be available. In terms of what those resources can do, you have to build a solution for the problem. We abstract all of them out and we take a task and then we specify an operation. What is the operation that you can do? You can double the content of a jar. How will you double the content of a jar? You can pour from a jar that has more water to a jar that has got some amount of water. Okay? Therefore, if you assume, for example, A less than or equal to B or less than C, well, less than, it's fine. How will you, what are the possible moves you can do? This is the only move you are allowed to do. Only operation you can do is pour from bigger one to a smaller one. So, you can pour from B to A. That way, B will become B minus A and A will become 2A. Or, you can pour from C to A. That way, again, A can become 2A and C can become C minus A, because from there you have poured over here. Or, you can do this. From C, you can pour to B. You can make B, because C is more than B, it is possible to transfer from C, right? And this could become C minus B. So, this way, you can keep pouring water from one to another by doubling the content. So, you always move water from a jar that has more water to a jar that has got less water, and how much you pour? Pour as much as the smaller one has, and thereby you double it. And now the goal is you have to empty one of the jars. You have to empty one of the jars. So how will you do that? It's a computational task, right? You have to do several operations and then you have to, so for example, I have 5, 7, 11. How will you do it? Try. Tell me what are the things that you will do to empty one of the box. From where to where you would move, how you would keep doing it, and then let me see your reaction. Let's interact for a couple of minutes and give me your suggestions as to how I would empty one of the jars. What are the moves you would do to empty one of the jars? You can prove from where to where. How much? How much, of course, is determined. You have to only double. You have already started doing algorithmic thinking. Okay? You are with me without knowing what you are doing. Now, how do I perform the operation to achieve a goal? You are now constructing a solution, right? Okay. Attempt. Suggestion, please. Yes. Initial condition is 3 jars with some water given like this. This is the initial condition. You are given 3 jars. One has 5 liters, another has 7 liters, another has 11 liters. Now you have to transfer the water according to the rule I told you. You can double the content of a jar by pouring the water from a jar that has more water into this. For example, you may make your first move to move 5 from the second one to the first one. You call that as ABC, let us say. From B to A, if you move, this will have 2 and this will have 10. Right? Because you have moved to 5 liters here and you have doubled it. And that has reduced the water there. It has now 2. and this has 10. What will you do further? Or is it a first move at all? A legal, valid move. Maybe this is a useless move, or this may not lead to a solution. We don't know. Right? Now we have to find a solution for it. So how do you think about it? What is the creative step you would do? Whatever the knowledge that you have. It doesn't require number theory or any other thing. Nothing other than common sense, and think about the context, situation, operation, and the task in hand. That's all. Yeah, participate, and then let's spend only a few minutes because we need to wind up as early as possible. Yeah. Yeah, what is your solution? First you move 11 to 5. That means you will have 6 here, and you will have 10, and this has 7. Then you can't move all the 11 to 5. On that you can move only 5, and that makes first one to 10, and second one to 7, and third one to 6. Then, yeah. Let us say, I will start like this. 5, 7, and 11. What is your first suggestion? C into A means 11 to 5. 11 to 5 will be, this will become 10 and this will become 6. Then I did 7 to 5. You want that to be done? Fine. Then this will become 10. This is 2. This 11 is intact. Then C to A. That means this becomes 20 and 2, and this becomes 1. A to, no, 2 to C or what? (19 to 2). Okay, so 19 to 2. Now, 2 you can transfer by doubling. So 1904. Excellent. You got one solution. Big round of applause. Now, first jar has got 1,987. One second jar had 8,45,543. Whatever is it, and then 777,964 liters are there. What will you do now? You have, earlier you had some 3, 4, 5, quickly you have come up with an ad hoc solution. This is how all problems are solved. How we solve a problem? In an ad hoc way. It will, somehow you solve it. Okay, it's like a fix, rather than a strategy or a solution or something like that. If it is a strategy or a generic solution, then we must have a very clear pattern of computation. That is important. Otherwise, you can't just, for example, your method is not generalizable for this. Now, look at the numbers. This, that's scary, and then doesn't give any clue whatsoever. And unless I have some meaningful way of visualizing in general a pattern of computation. So observation, you made it right, observation. So I have to do a pattern of computation. Pattern of computation in computer science is called the paradigm. Para means external, daima means example. It's a Greek word. Paradigm, externally displayed example to show a pattern, paradigm. Okay, so when you go to a cloth shop, outside there is a doll on which some new kurta and pajama would have been there, and then you know that that's exactly the kind of new arrivals in the shop. That's paradigm. Paradigm is going to show you a pattern. For us, it's a pattern of computation. What kind of paradigm or what kind of computation will work? That is where that art of computing begins, right? In order to solve the problem, what kind of paradigm will be useful for us? If a paradigm is chosen, how do I apply it for this context, right? That's another thing that we have to worry about. How do we apply it? And so on. So in mathematics, we have several computing techniques. They have all become excellent algorithm design strategies in computer science. Beautiful strategies. They have thought about a lot. Mathematicians have got much broader range of questions answered. They have asked questions on existence. Right? Continuous differential function, there exists a theta such that f dash of theta equal to f of b minus f of a by b minus a. You know this, right? Mean value theorem, Rolle's theorem, several theorems are. After reading the proof, if I give you the function x cube plus 7x plus sin x and the interval 43, 221, will you be able to find theta? Mathematicians have convinced you that there exists a theta, but did they tell you how to find that theta? For computer scientists, what is very important is it should be a computational procedure. Mere guarantee of existence or a logical argument of existence, with that I can't design an algorithm, explicitly computable steps. So I need a computational pattern, not only a logical fact. I need that fact. In addition to that, I need constructive solutions. So I have to go about doing something constructively. One great idea mathematicians have is called method of iterated improvement. That is how Mother Nature does to us naturally. You get a cut or a wound, what happens? Over a period of time, it heals. Every day, some part of it is getting healed and finally it gets healed. Method of iterated improvement. Okay? Gradually, things should be made better and better. Can we have a computational process in which certain things can be made better until I reach the goal? Right? I keep improving. That means I need a progress monitoring or progress indicator parameter or something that tells me that, hey, you are doing a right thing, you are progressing in the right direction, go ahead like this, you will hit the answer. I need that kind of a computational process. Once you see this as a paradigm, you have a starting point to think, right? Whether you succeed with that or not is a different question. But at least when I wrote those three numbers, you are completely clueless. How do I go about what do I do now? Was your predicament. But when we say, let us apply a strategy, let us do the algorithmic thinking, let us have a pattern of thought guide us. So, I'm going to talk about method of iterated improvement. Something should become better and better, and that should lead to the answer or to your goal. How do we get that? Okay? So, what I'm going to do is, there are three jars. There is some jar that has got minimum amount of water. For example, 5, 7, 11. In this one, 1, 9, 8, 7, whatever. So there is some jar that has got some minimum amount of water. I mean, among the three that has the. Can I do some operation and then reduce the minimum amount of water in a jar is smaller than that? Is it possible for me to reduce in such a way that it has come down? If I have a method to do that, I can iterate it repeatedly. Then the jar that has got smallest amount of water will have now less amount. And one more, again it will become less. And it will become less and less and less, and it will hit 0. Is it okay? Is that all right? I start with some integer. After something I made it smaller. Then another integer that is smaller. Will it hit 0? Not necessarily. See. Huh? It can skip 0, but that is not going to happen here because we are going to use only the water if it is available. So let us assume that we have only positive integers or non-negative integers. In a non-negative integers, if I have a sequence of reducing numbers, it can hit 0. You can keep on reducing it, but then it has to stop at 0. So if your goal is an integer should become 0 by some process, a good strategy is method of iterated improvement where I'm going to make the things smaller and smaller and smaller and hit 0. Right? This is called the well-ordering principle for integers and discrete math. You might have done this. This is equivalent to simple induction, strong induction. Have you done that, honestly? Huh? Well-ordering principle. How many of you know what is well-ordering principle from your discrete math course? No, you should not raise hand. Okay, so learn mathematics first very well. That is important for computer science algorithm. First you have the natural intelligence, then you can go for artificial intelligence. First you learn and then make the machine learn. If you don't learn well, how will you make the machine to learn well? So get discrete math well and know those principles. So let's see how to make certain things smaller. Let's take another simple example. 10, 2006, 206, 287, some number, 3 numbers. Now the smallest jar has got 10 liters. I want to have a configuration where the smallest jar has got less number of. How do I make that less? Now you see that by transferring, I keep removing. If I move, I will move 10. If I again move, I will remove 20. Therefore, I am removing multiples of 10 if I am using 10 as a base and keep reducing the content of other jars. So, let me take as much as possible. For example, from 206, I remove 200. That is quotient and remainder theorem. Okay? A equal to QB plus R. So, quotient and remainder. Tens, I am going to use to remove. The remainder is a smaller value. So, my target is, I will make sure that I will have only 6 in the second one. How will I have 6 in the second one? I have to remove 200. How do I remove 200? I can remove 200 only by doubling process. Not simply, I can't pour 200 out of it. Okay? So, I have to remove 200, which is 20 times 10. 20 times 10, I have to remove by a doubling process. So this is where, as computer scientists, you can immediately see, if I use the binary representation of this, I'm not going to scare you with zeros and ones. This is simple number. So this is 16 plus 4 is 20. These are the powers of 2. Right? So you can have binary representation 1 0 0 0 1 0, whatever. So this much is to be done in the doubling process. So when I make the 10 into 40 using the doubling process, I get an opportunity to empty 40 from the second one. When I make it 160, again I will be able to transfer 160. This is what I'm going to do. Okay? For example, 10, 206, 284. Quickly let me do. I transfer 10 from here. That makes it 20 and 274. Again I transfer 20. That makes it 254. And this is 40. Now I can remove 40. Therefore, when I remove 40, it becomes 166 and this becomes 80. And again, I move 80 from this. This is 257. From this, when I move 80, this becomes 177. This becomes 166. Now I get an opportunity to move 160 and this becomes, this becomes 320 and this becomes 6 and this becomes 177. Now you see that I have a configuration in which the smallest jar has got definitely less number. Why it is a less number? It is a remainder. When you divide some number with another number, remainder will always be smaller. I have a guarantee that when you do this, I get something smaller. So what is that I have done? I have taken a kind of binary representation because it is a doubling process that is involved. And doubling process is to be done, and I can't simply pour. I have to wait for the right opportunity to move right doubling, copying of that. Because 20 is 16 plus 4, when 4 times the jar is available, I can move 4. When it becomes 16 times, I can move it. Therefore, and how do I make that 4 and 16? I use the third jar. The water from the third jar is going to be used to bring it to the appropriate power of 2, and then using the binary representation, I would transfer it. So put in very simple ways. Yes, I have only 5 more minutes. Therefore, what I have to do is that if you look into the binary representation, when there is a 1, you transfer from here. If it is a 0, you transfer from here. So you take a quotient of B with A and just check the binary representation, and with that you will be able to simply get the job done. Now, this strategy works for any set of 3 integers. Okay? And definitely the smallest jar will have less number of water. Now have it as the same target. Make sure that in your transferring process, you have something modulo or remainder of 6. And this process converges. And definitely you can empty it. Okay? Now you have a general method. You have a method based on method of iterated improvement. Method of iterated improvement is applied in a customized fashion to solve our problem. In that way, for whatever the problem that you have, you see that, and this is exactly what is done if you know graph theory and bipartite matching and so on, which has an application in some real context, job scheduling and allocation of the resources to the requirement. Method of iterated improvement. You start with a small matching and make it into a bigger matching and bigger until you get saturated, then you finish the job. How do you improve the iteration? That depends on the graph theoretic steps and so on. In general, this is one of the very powerful ideas. Like this, you have lot of interesting paradigms or ideas, and that constitutes the body of design of algorithms. The second important thing is, you may come up with a method. Mathematicians are very happy if it is finite, but computer scientists are not happy if it is just because it is finite. They are not going to stop at it. One important part of the algorithmic thinking is how efficient is your solution, how good is your solution. So you might have done certain number of transfers, and then you might have come to a configuration that has 0 liters. Can you achieve the same thing with less number of transfers? This is the concern of computer scientists. This is a part of algorithmic thinking. It's a part of computing because you are going to use a physical resource. It is going to use time, memory, communication, bandwidth, lot of things it will use because you want to implement it on a physical machine. Physical resources are consumed. Therefore, we are interested in reducing the so-called complexity. I'm not only interested in just some method that solves, I'm interested in that method which has. That is the reason why computer scientists are worrying about the complexity, data structures, and various things. These data structures is not a concern of mathematicians. It's purely worry of computer. How do I organize the data so that each operation I can do effectively and solve the problem? How do I use randomness as a resource to arrive at the answer quickly? If I have no hope of solving the problem effectively, can I use randomness? Can I get nearly good solution? Approximation algorithm. Everything, if you look at it, the goal is on the performance. The goal is on the efficiency. Okay? So, how much time? 0 or 2 minutes. That is a lot more time. I have run out of ideas, actually. Thank you very much. Limiting for 2 minutes. So, algorithmic thinking is computer-based problem solving, arriving at a solution that is a computational solution, using paradigms or pattern of computation to design a solution. Then you evaluate how good is the solution by looking into its complexity. When that is not satisfactory, you try to discover more efficient solution, more efficient paradigms, and so on. And the creative journey begins, and this is a never-ending journey. Okay, the life is full of challenges. There are always problems that will escape the limitations, that will escape the creative limits of human race and remain as open problem for ever and ever and ever. That keeps the human mind ticking, live, excited. Join the exciting journey of area of research in Joy of Algorithms. Welcome to the field. I end at this point. Questions, please.
Yes, it's time for questions.
Yes, there are questions. Well, NP equal to P. Oh, if only I have the right view, I would have been millionaire by now. It's an open problem, and it is unlikely. In fact, I am sharing the opinion of 1,000 others. Most of the people by now believe that if a problem is NP, there is no hope of getting a polynomial time solution. It looks like that's going to be the case, most likely. Yeah.
So in this given problem, right, you gave us the constraint that we can only pour into a bucket if it's less than or equal to. Imagine we make it strictly less than. Is it still possible to solve it?
Which is strictly less?
So if you want to pour water into a bucket, the bucket that you're pouring the water into, it has to be less than, right? Less than or equal.
Less than or equal to, yeah.
What if we make it strictly less than? Is it can we arrive at a possible solution?
In that case, you will end up with the two buckets having equal configuration. In order to empty it, you can do it only by transferring from equal buckets. So you won't end with 0, but you can definitely end with, in our earlier solution, 2, 2. Some number 2, 2 was there, no? After that, you can't go to 0. That's all. But the final state will be 2 buckets with equal amount of water, if it is strictly less. Yes.
Understood. Thank you.
Pandu?
Yeah. Ah, yes, please, go ahead.
So if somebody settles the PNP question
Yes.
and shows it's not equal, you won't be impressed?
No. I have to change my career to agriculture because right now I am working in cryptography where the security
No,
of
I said
several
P not
problems
equal
are
to-
depending on the P not equal to NP.
So I meant P not equal to NP.